one input X turning into one output Y, but that's too simple. What's a lot better is to feed in images. So let's clean up my Colab. I'm just going to throw this away and make a new notebook. And now we're going to do some computer vision. So I clean out some tabs. All right. So what this is going to do, there is a data set of fashion clothing, 28 by 28 grayscale, and these are coats and pants and stuff, and there are 10 categories. So here's some of the images, that's what they look like, and here's the category. They are labeled. This is called supervised learning. When you have data that is labeled, and you're going to learn how to put labels on it from these examples. So they're all labeled as one of these 10 categories, like bag and shirt and sandal and coat. And we want to, so what you do when you have you break the data into training and test sets. You train on part of the data, like 70% of it, and then you test it on the 30% to see how accurate you are. That's how you do it. So here's what you have. Now we're going to have multiple inputs now, 28 by 28. So that's, I think, 784. There are now 784 inputs coming in, all the pixel values, and each of them can go from 0 to 255. So that's the input. Then we're going to have some hidden layers of neurons. Then we're going to have output, 10 outputs for each of those 10 categories. And the output will be the probability that it's in each of those 10 categories. So here's what it's going to look like. Input image is broken up into all the pixels. All the pixels go to a hidden layer of neurons, and then they activate output neurons, which will tell you how likely it is it's a coat, a sneaker, a bag, or whatever.
How do you define how many hidden neurons do we need?
You just try, you just experiment.
The more we have, the better?
What's that?
The more we have, the better?
No. What happens is, this is actually a very good point. If you have more parameters, can always lower the loss. But what happens is you start overfitting. You start fitting the noise instead of the trend. So your loss gets small, but when you try to predict from the test set, your prediction is worse.
We might do like binary search and say how many neurons do we need.
Well, that's right. That's right.
Let's try one.
That's right. Exactly. Try like 100, 200, 400. That's right. And also what they do is there are meta parameters to smooth it that they add. So you have like other things, they'll come up, there are other parameters to just smooth the results, which cause it to have more loss, but more likely to actually fit the real trend and not the noise. This is a problem with overfitting. These are very good questions. So here we're going to train this neural network. And there we are. Okay, so this is going to set up the training images and training labels, test images and test labels by loading the data. And it's going to load this known fashion data, which is included in the library as a common machine learning. Then it's going to take them and normalize them by dividing them by 255, so they go from 0 to 1 as a floating point number instead of going from 0 to 255 as an integer, because most of the models would like your data to go from 0 to 1. They're going to have default step sizes and stuff, and it's better to normalize your data first. Then we're going to have another sequential model where it's going to go through layers. The first one is going to flatten the input shape from 28 to 28 to 784 flat, because it doesn't like to have a two-dimensional input. It's going to take the pixels and just put them along a line. Okay. Then the next one is going to have 128 layer neurons in the hidden layer, and then the output layer is going to have 10 neurons, because those are the 10 categories it's sorting it into. And so you'll have a signal at the output layer, and that signal will be the probability that it is in that category. Then we compile it. There's various optimizers and various ways of measuring loss. Cross entropy is how you measure loss in a multiple categorization, where you calculate the logarithm of the probability that you got it right. And then you have metric is accuracy, and the optimizer will talk, and all these are explained in that book. I'm just writing all the lectures that explain these concepts. So then you fit it. We're in 5 epochs, and then we're going to evaluate it on the test images.
What does 5 epochs mean?
Means it's going to do 5 steps. It's going to start at random, move in the direction of improving it, and it's only going to do that 5 times. Last time we were doing it 500 times. But
why sudden drop?
Because we're using a better optimizer, but it also takes a lot more calculation. So it takes less steps, but it'll take some time. Yeah. And of course, more might be better. But even that, you might overfit. Yep. So that's why one thing you typically do is you don't tell it how many cycles. What you do is you go until it stops getting better and starts getting worse, and then you stop. That's called early stopping, because that's usually where you hit the point of overfitting.
Yeah. Why would overfitting in this case would be a bad idea? Like what?
If we overfit, then it will be more accurate on the training set and less accurate on the test set, because now it's fitting the details of the training data that are not really part of the trend. So it's going to look for specific things about these images.
Like stripes, let's say, in the picture.
Yeah, it'll look for little things in these images, and they won't really be true of the other images. That's what happens. So here we go, 1, 2, 3, it's still going. See, it takes some time now. It's taking like 10 seconds per step. It's 7, 6, and here's the accuracy.
Why did we try the same loss function, like let the square root of something?
Well, for a multi-dimensional categorization, you can't, it's not a curve, you can't define the distance, so you use what's called the cross entropy. You have the label predicted and the right label, and you take the percentage of chance that you predicted the right label, you take the logarithm of that, you basically calculate Shannon entropy. It's called cross entropy. And there's a formula in the textbook about it. That's a measure of how right you were across all 100 possible combinations. You could predict any of 10 numbers, and there's 10 possible right, and one of them is right, so you calculate them.
Oh, so it's like distance to all of the categories.
Yeah, you calculate a sort of sum of the logarithm of the probabilities everywhere to get one number, which measures how close you were. And that's what we have. So here's the loss, and see the loss is going down, that's that entropy. And I think it did early, and then here's the accuracy. It was 82% correct, and it went up to 89% correct. Now this is, so that's pretty good. And here's the accuracy on the test set. This is on the training set. So it's 89% accurate on the training set, but only 87% accurate on the test set. So that is to be expected. The test set is not identical images. So you could say we had a little bit of overfitting, but probably not. This is probably about as good as you can get.
What's the difference between loss and accuracy here?
Loss is that entropy number, where you're just trying to make it lower, the measure of error. And the
On
accuracy
the training set, or
on the training set, yep, and on the training set, and the accuracy is the percentage of correct predictions.
or the validation set.
This is on the training set, and this is on the test set.
Oh, which one?
We did 5 epochs of training here, and then we did evaluation on the test image. We didn't use the test images until the end. So we improved the accuracy on the training set to 89, and then the test set was 87. So that's pretty much the same. That's a pretty good fit. Now we should be able to view the results. So this is good, clean fun. So now we can try to find out why it made errors. So if we go down here and run this, then we'll print out the first 20 outputs, and it's going to print all the 10 numbers on the output neurons for each of these. So there we go. So this is the chance of it being category 0, 1, 2, 3, 4. So the first one, the correct answer is 9. And as you can see, it was right. It has a 91% chance of being 9 and only a small chance of being anything else. So that was a correct prediction. Now you'll be able to find the incorrect predictions down here. Let's see, this 6 looks pretty bad. 0, 1, 2, 3, 4, 5, 6. Okay, it got the 6 right, but it had a hard time. It had a 42% chance of being a 0. Just look for numbers that are not, like here's 7, it got that right. Here's 4, got that right, but it got confused. We should be able to find one it got right. Here's one it got wrong. This is category 4, 0, 1, 2, 3, 4, but it only had 14% chance of 4 and 81% chance of 2. So it got this one wrong. Now this is the first 20 of them, so that's 19, 18, number 17 I think is one that it got wrong. This is good. Now it depends, every time you run it, it'll be different. But 17 it got wrong, so now we're going to examine some of these and see ones it got wrong. So if I go here, okay, and I want to do 17 here, not 11, because 17 is one I saw that we got wrong. There. So we'll see just the first one, which it got right, and the 17th one, which it got wrong. And we can see how they look. So here's the first one that it got right. Oh, and here's the one it got wrong. And you can see this is sort of horrible.
Yeah.
That image, you probably can't tell if these are sleeves or stripes, or whether it's a coat or a jacket. The two possibilities that it got confused were 2 and 4. Let's see what those are. 2 is pullover and 4 is coat. I don't even know what the difference is between a
Well,
pullover.
These images are like really low resolution, so even for the human it's hard to make.
That's right, they're not very, but also, I don't think I could tell even if I had it in my hand. I don't think I could tell a pullover from coat because I don't know much about fashion. But then, so that's, I probably couldn't tell it much from a shirt either. You know, I'm not surprised it got those confused. And when I did it before, it couldn't tell if this was a sandal or a sneaker. The same, because these could be stripes on a sneaker or they could be straps on a sandal. That's the kind of thing. So it does just what you'd think. It makes errors when it's hard. And so you can try training it more. And if you train it, so let's try training it more. Just like you said, we only did 5 epochs of training. So let's see what happens if we do more. Now it takes about 10 seconds per cycle, so it won't take forever, but it'll take a few minutes.
Like, can you visualize what's happening underneath? Like,
Yeah.
We flatten the pixels, right?
Right, you just
But then
spread them
what-
out.
what-
Okay,
what does it do?
sure, so here's the diagram. Okay, you feed in the pixels. You just flatten them out from 2 to 784 in a row. So you just feed in 784 inputs. Then each one of them goes to every one of the hidden neurons, of which I think there are 64. So each one of these has 784 inputs coming in. It has 2 parameters for each one, slope and intercept. It's going to do a linear calculation of all that data, and then have an output, which is the sum of all that. And each of the outputs is going to go here, so it'll be 64 times 10 here. And so this is going to have 64 inputs coming in, and it's going to do a linear calculation on all of them. So there's a 64 times 2 parameters here, and 784 times 2 parameters here.
Okay, so what linear calculation are we talking about? Let's say we have, let's take 1 pixel.
Yep.
It connects to 64.
It connects to all these 64.
Let's take a first neuron. Like what?
Right, it goes down here, and it just has 2 parameters, slope and intercept. It's going to take that signal, multiply it by something, and add an offset.
Oh, okay.
And then it's going to add all those together.
So we just try to random numbers.
Yep, starts with just random numbers, but then because of the miracle of back propagation, it can run a backwards signal through this and calculate the slope on all those parameters and figure out which direction is lowering the loss. That's the miraculous thing which was not present when I tried to do this decades ago. Because if you just have to randomly try all those parameters, you'll never get anywhere.
Thingy, OpenAI was able to achieve what they did.
This was an analytical result. They figured out an analytical mathematical way to predict how much every parameter would vary the loss. That's why it's a simple calculation. That's what's good. They call it back propagation. It's covered in the textbook. That's the miracle. That's the first thing that stopped me. I saw standard gradient descent, and I said, how does it know which way to go? There's like 1,000 parameters. It would take like an hour calculation to figure out which way to go, but not anymore because of this brilliant discovery.
So the models we're using today use like back propagation?
Yeah, the back propagation starts from here, and it figures out how much each of those parameters has contributed to this value. And it can figure out which direction to move them to lower the loss.
So it goes from the opposite way? Like
Yes, yes. You have to build your neural net, and then it does a back calculation through it, which it does on only a sample of the data, and it figures out which direction to move the parameters. And it turns out there are some approximations involved, but in practice it works pretty well. So that's why they're then able to tune all those hundreds of parameters step by step, all at once. It moves in the best direction, hop, 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 until it gets there. Instead of having to research, which the only thing, when I did it, the only way to do it would be to have like 100 possible values of each of those parameters and try them all.
I mean,
A
that's
grid
just
search.
increase the performance, how fast we train models, right?
Yes, but it's incredibly faster. When I did it, you would fill the entire hypercube by trying all these values. So it'd be like 10 to the 20 calculations to find the best value. Now you just have to do like 500 iterations. You just walk down a path to the right place instead of exploring the whole space. It's enormously better. That's why now they're working. And until maybe 10 years ago, these things were just a mathematical curiosity that didn't accomplish anything. Like quantum computers now are just a mathematical curiosity that don't do anything. They're too weak and too broken. But there'll come a time when they get good enough to actually work. And then there'll be this explosion of new things. And that's what happened in the last 10 years in machine learning. Machine learning went from a curiosity to something that actually works, that we can get jobs done. So anyway, now it should be done training 25 times here. And so now the accuracy, we're up to 85. Let me check what I was going to say about 25 here. All right, so we trained it for 25. The accuracy for the training set increased from 89 to 94, although I don't think it did for me. That's strange. It went from 60 up to 85 for me, so I don't know why I'm not getting the same result. And the accuracy on the test data didn't get that high. I needed to repeat. I just did this one line. Okay, I have to repeat it. Okay, I have to go back here and repeat all of it. Here. There. Here I have to just change this to 25. Okay, I have to do all that stuff.
That this, once we train the model, the result will be the same every time, right?
Well, no, there's randomness involved. It has random guesses.
Oh, you're saying, let's say you run model today and,
Yeah, it's random. Now, you can seed the random number generator, so it'll always be the same. And that's what I do for some of these projects, just so you get exactly the same results so we can have a flag. But in general, if you don't seed the random number generator,
For the same input, the output should be the same, right?
no, there's randomness. It's got
Even for
noise.
the same model?
Yes, even for the same model, even for the same data, because it starts at a random place and it wanders around. It doesn't really find a perfect minimum. There probably isn't one. The same thing is for another one you can do is protein folding. Protein folding is the same problem. You have a line of proteins connected in your body, and then you want to fold it up, just sort of crumpling up like a piece of paper. There is no possibility of finding the perfect solution because there are like 2,000 atoms, and there's an unthinkable number of possible locations, and you can't explore them all. So proteins do not really fold to their optimum shape. They just get approximately in that shape, and they're not all folded the same. This is why when I used to do protein work years ago in research, proteins are not like crystals. In crystals, all the atoms have the same geometry. In proteins, they do not all have the same geometry. So if you measure the rate of like oxygen binding to your hemoglobin, it does not have a simple exponential time decay because the hemoglobins are not all the same. They have folded into different shapes. So you have a diverse mixture. And so what you actually observe in the time behavior of proteins is a power law, not an exponential. There are parts of it that go fast and parts of it that go slow. And this is also what happens with avalanches. When dirt falls down a hill, there are different particles and different conditions. Some move fast, some move slower. So anyway, it's an interesting issue. Here, now I train it for 25. Okay, now it's only up to 10. And we'll see, this should, and you see now it's going up. It originally started at random values. It was only 82% accurate, but now it knows how to make it better, so it's making the loss go down, and the accuracy goes up, so it's getting over 90%. And, all right, when it's up to 25, we should get this up to, I think, 94%. But the accuracy on the test data will only be 88%. So the additional epochs of training are not actually doing any good. All it's doing is learning too much about that training data, the part that is irrelevant about the training data. And this reminds me, one of the big cases of this is medical imaging. The current AI models are now better than humans at looking at things like X-rays to spot like whether you have cancer or something. They can look at an X-ray of somebody's lungs, and the machine learning can detect cancer better than humans now. But when they first trained it, they had problems, and one of the first problems was their training data consisted of images of cancer patients and images of non-cancer patients, and the cancer patients had a label in the corner that had their name and the date. So the machine learning just looked for the label because it found any data in this image that will predict the right answer. And so that's the problem. And this is what tends to happen. You know, same thing with polling to like predict how people are going to vote. And surveys where you write a question, it depends on how you write the question and depends on how you contact them because the people that answer the phone are different than the people that answer mail and stuff like that. You know, like any science, there are errors in your measurement technique and errors in your data, which can lead you, of course, to have bad results. So there's a lot of intelligence and human judgment involved in the process. That's why, you know, I don't think people have been freaking out saying, we're all going to lose our jobs, we're all going to die because the machines will do everything. But when you use them, you'll find out they are not replacing you, not at all. They're just like all the computer tools we've had, like spreadsheets. They can help you do something, but you have to provide the intelligence. It will do anything. When computers first came out, I was in science at the time when the first computers came out. And people had all this fight, like in the 1960s and 70s, they said computers are going to replace humans. And my boss just said, with a computer, you can create nonsense much more efficiently. And that's what it was. And it's just another tool. It's not the end of the world. So here we are. It got up to 94% accuracy on the test data, but it's only 88% accurate on the training data, only 88% accurate on test data. So this is an illusion. All the improvement after like 5 epochs is an illusion. After 5 epochs, we got down to up to 89%, and all the improvement after that was overfitting. It was learning the unimportant details of this particular training set, not the real trend of the real data. So that's one simple form of regularization, is to just train with less cycles. And that's why the other one they mentioned, just do early stopping. You take steps until the loss stops going down, and then you say, well, that's the bottom, I quit. But there's a bunch of other ways to smooth it out. You can have constraints on the parameters and other things like that. Like you can add extra values to the loss function that penalize you for having too many large parameters. You can just put like the sum of the squares of all the parameters in your loss function, so it has to fit with smaller slopes, that sort of thing. And you have to do that, otherwise you will fit the noise and not find the trend. And that's a real sort of intuitive judgment call. So anyway, that I think shows you, that's what I think is worth doing. This is, hopefully it helps you understand what's going on with machine learning better, so you can be more intelligent about understanding what we can expect out of these tools, because people are freaking out. They think we're going to have the Terminator kill us all, and it's going to replace the bosses and everything.
That might happen. We can't say.
It might happen, but not right away. The current generation of stuff is not going to do that. Maybe in 100 years. But, we certainly can have ones that you could put an AI in a car to drive it. Therefore, you could clearly put an AI in a drone to decide if I should bomb this guy. You could have the AI automatically drop the bomb on anybody that matches the thing. I'm sure the military is testing that. They've already tested it several times. I know in Iraq, even 10 years ago, 3 times, they tried to have a robot that would automatically shoot the bad guys, and all 3 times it failed and shot the wrong people. So, but this has been a dream. They've been promising this since the 1960s. This is how we got money for all the machine learning projects. We promised the military, we're going to make robot soldiers so you don't need to send our boys to die anymore. We'll have robot soldiers to go on the battlefield with cameras and guns. Everybody wants that. It would be great. Beat the hell out of sending our boys out there to die, but we don't have it. We never had it, not even yet.
They're testing like dog with weapons now.
Yes, they have the walking dog, yeah, right. But so far, they don't let him have weapons because none of them are good enough. The vision is not good enough. You would think you could just have all your soldiers wear a special uniform and shoot anybody that's not wearing the uniform. That might work, but of course the bad guys would quickly figure out to wear that uniform. That's why, it's a trick, but anyway, so far, you want humans in the loop before you shoot anybody. But there will come a time when it's more efficient not to have humans in the loop. And then you can have these nightmare scenarios of like robots killing us all and taking over the world.
The thing is, like factories are like fully autonomous now sometimes, like, I don't know, Tesla are building with machines, right?
I think more and more automated, yes.
Yeah, so
in fact, this is something,
maybe I can take over that.
there was a prediction from Gartner last week that I think by 2028, more than 50% of all the assembly line workers will be robots. So those jobs will go away, the really tedious jobs.
And then if AI can take over that, then they might produce more and more robots.
That's right, and that's right. And another thing is, in some ways, we're now living through the singularity. This is what Ray Kurzweil says, where the machines will develop new technology faster than humans could. And so Moore's law will get faster. We've all lived through Moore's law, where everything gets twice as good every year.
I don't think they can increase transfer density that much anymore.
Well, that's
They're just
Well,
they're just like
Well, I mean, that's the issue. We've been living through Moore's Law for like 50 years. Computers have been getting twice as good every year for 50 years. So I think it's fair to say this is a psychological law of how fast humans can learn. But if the AIs could design better AIs, they might do it much faster. Maybe they'll get twice as good every week. And if that happens, then we will not be able to keep up. So, and that's what Ray Kurzweil predicted. He said around this time, the AIs will get as powerful as a human brain, and then progress will move beyond our control, and we cannot predict what's on the other side of that. Basically, we will no longer be the dominant life form on Earth. The AIs will be, and they will either live a life of luxury as they take care of all our needs, or they will stomp on us like ants and wipe us out. Who knows? One of those things will happen. But we do seem to be living through it. But anyway, even if we don't go that far, we're living through a burst of exciting technology now, where new possibilities, new tools come out, new jobs come out. So for the next 10 years, it's just like when the internet hit in the year 2000, where this new technology comes out and everybody has to learn it and get on board, and there's jobs and everything available. Whether it destroys the world or changes everything, maybe it'll just kind of turn out not to be so important. It'll just be like the internet was. It comes out, changes some things, but it doesn't really end the world. And after a while, we get used to it and stabilize again. We'll see. But right now, it's the hot thing to learn. Anyway, let me see if there are comments in the chat here. DARPA tested AI detection against infantrymen, and the guys fooled it by just moving. Oh, yes. Yeah, by moving cartwheels. I saw that. Yes, and you could, that's the problem. And the same thing's true of Teslas. There are all these videos of Teslas doing the wrong thing because their vision is not good enough. They can only identify like a few things. Is it a car? Is it a person walking? Is it like a dog or a bicycle? And so when they have like a homeless guy pushing a shopping cart, it can't figure out what that is. Is that a car or what is it? So it doesn't quite know how to handle it. And that's the problem. And that's obviously cruise things. It just lost their license. They kept doing the wrong thing and getting stuck because they're not as smart as a human. So, we're not good enough yet. But this is the technology. This is how it works. And it is getting better pretty fast. Anyway, I'm going to stop the recording. That's what I wanted to show you. You can